Everyone, welcome back to the channel. This is the continuation of classes on quantum mechanics. In our last video, we have derived the mathematical expression for calculating radius of an electron which is present in the nth orbit, right? If you have not seen that video, the link has been given in the description. You can look over to that video. Okay, so in today's session, we shall discuss about the expression for calculating energy of an electron which is present in nth orbit. So this is the most important expression required for the quantum mechanical understanding regarding the concept of atoms. So without delay, we shall continue first expression for evaluating the expression for energy of electron present in nth orbit. And if you observe, here we have considered an electron which is present at a distance r from the nucleus, which is having the charge Ze, okay? And the electron is revolving around the nucleus in circular path with a velocity equals to v, right? So since the electron is continuously revolving around the nucleus, so the moving electron will possess kinetic energy. And since the electron will be at a certain distance from the nucleus, and because of its height from the nucleus, obviously it will possess a definite value of potential energy, right? So the electron is possessing two types of energies, that is potential energy, which is because of its height, and kinetic energy because of its moment around the nucleus. So if you want to calculate the energy possessing by an electron which is present in nth orbit, we are supposed to take as total energy, okay? So then we can write it as the total energy of electron, because it possesses both potential energy and kinetic energy, okay? So the total energy of electron will be taken equals to E, and that will be equals to arithmetic sum of potential energy and kinetic energy, okay? And we know that the value of kinetic energy is equals to half mv square. This is the mathematical expression we will be given for the kinetic energy, provided m is mass of the electron and v is the velocity of the electron. And we need to calculate the value of potential energy. And remember one point, if you consider the position of the electron at infinite distance, okay? So by definition, what we can say, it is the energy of an electron when it is present at a distance r from the nucleus, right? So the potential energy of the electron can be calculated just by the value of the work done of that electron from infinity to that particular point. Because the electron is present in nth orbit, so we used to say that the atoms are present in three-dimensional space. So the electron should reach to that particular point from infinite distance. So that will be considered. And in moving from infinite distance to a particular point, means to a distance of Rn, it has to perform some work, right? So that work will be taken for the electron, that is work done which is performed by the electron. And we know that the expression for work done will be simply, it will be the force into distance traveled or distance covered or displacement made by the electron. And force, that nothing but electrostatic force, that can be given as Ze square by r square, right? And the distance covered by the electron will be taken equals to dr, right? So let me consider this as equation number 1. But here, as we said, the potential energy of the electron should be calculated. But when the electron is at infinite distance, the potential energy will be 0. Right? But here we need to calculate the potential energy of the electron at a distance r. So in order to get the exact potential energy value, whatever the work done expression here we have framed, this has to be subjected to integration between the limits r and infinity, because we said that the work is done by the electron in moving from a distance of infinity to the distance of r. Right? So the limits should be infinity to r. So we need to perform the integration. So integration of Ze square by r square into dr. Between the limits r is equals to infinity to r is equals to r. So by performing the integration, we will be getting the exact value of potential energy of the electron which is present at a distance r. Okay, so if you perform the integration, so z will be a constant, e will be a constant, so only a different integration will be done for r square. So it will be, so we know that integration of x power n into dx is equals to x to the power of n plus 1 divided by n plus 1. This is the integration value for x power n. So here what we are having r square, when it is taken to the numerator, it will become minus. So z e square r to the power of minus 2 into dr. So this will be the equation, and this has to be integrated now. Okay, so z e square will remain as it is. So r to the power of minus 2, if you apply the same concept, that is x to the power of n, the value of n will be minus 2. So r to the power of minus 2 plus 1 whole divided by minus 2 plus 1. Right. So this will become, so minus 2 plus 1, it will be minus 1, and minus 2 plus 1, minus 1. So the whole term will become minus z e square, and here you will be getting r to the power of minus 1. Or else you can take the r to the power of minus 1 to the denominator, so it will become z e square by r. Right. So here I have applied the limits directly, because if you apply the limit infinity, it will become 0. Then the upper limit will be r, that has been taken directly over here. So the actual potential energy value of the electron at a distance r is given as minus z square by r. Let me consider this as equation number 2. Okay, and as we said, the electron is moving around the nucleus in circular path, right? So before to that, we have said that the total energy E is equals to kinetic energy plus potential energy. So here we got the value of potential energy, and the value of kinetic energy is known, that is half mv square, and potential energy is minus z square by r. Here we have the plus into minus it will be, and the value of potential energy is z e square by r. But here we should know the value of mv square. Okay, so to get the value of mv square, once again we have to go with the help of the same expressions that will give the value of centripetal and centrifugal forces. The reason is, in the last video we have explained that during the derivation of expression for radius of electron which is present in nth orbit, if the electron has to be present at a distance r specifically, the centripetal force experiencing by the electron should be exactly balanced with centrifugal force, right? The same condition will be taken over here in order to get the value of mv square. Here we have given the mathematical expressions for centripetal force and centrifugal force. Centripetal force is given by z square by r square, and centrifugal force is given by mv square by r. So when these two are exactly equals to each other, then the electron will remain in the orbit. That means will not fall into the nucleus and may not go out of the orbit. So when these two are equal, z e square by r square, that's equals to mv square by r. R and square will get cancelled. So here we will be getting the value of mv square. So mv square is equals to z e square by r. Okay, so this is the expression number 3. So if you apply the same value in the total energy expression, that is E is equals to Ke plus Pe, at the place of mv square, we will take Ze square by r square. So total energy E will be 1 by 2 into Ze square by r minus the value of potential energy is once again Ze square by r. So here we have 2r and here we have r. And as we said, the r will be the radius of nth orbit. So we can take it as rn. Okay. So now here we have 2rn and here we have rn. So we can take the LCM. So when you take the LCM, 2Rn will be the LCM, and now so 2Rn will get cancelled. The only one thing that remains is ZE square, and here it will be minus. So Rn and Rn will get cancelled, will remain with 2, which will be multiplied with ZE square. So you will be getting minus 2ZE square. ZE square minus 2ZE square, you are going to end up with minus ZE square divided by 2Rn. That is a value of E. Let me consider this as equation number 4. And now we shall continue further for calculating the value of energy, expression for energy. And here we can notice that Rn is there. We know that Rn is the radius of nth orbit, right? So since Rn is equals to n square h square divided by 4 pi square z m e square. So this is the value of Rn, and let me consider this as equation number 5. So in order to get the complete expression for energy of nth orbit, we need to substitute the value of Rn in expression number 4. That means substitute the expression 5 in expression 4. So the equation will be square by 2Rn into, so value of Rn will be substituted over here, right? So En is equals to minus ZE square whole divided by 2, and we have n square h square. So denominator will goes to numerator over here. So into 4 pi square z m e square. So this is the complete substitution of the value of Rn in equation number 4. And here 2 1s are 2 2s are, it will get cancelled. So here we have 2 z terms. There are 2 e square and 1 m. So as a whole, the equation will finally turns to En is equals to minus 2 z square pi square m e to the power of 4 whole divided by n square h square. So this is the finalized expression that we can give for energy of electron in nth orbit. But here pi is a constant, m is mass of the electron, E is the charge on electron, and h is Planck's constant, n is the shell number in which the electron is present, and z is the atomic number of the atom. By substituting the values of all the constants, say the value of pi will be 3.142, and the value of m, that is mass of the electron, is 9.1 into 10 to the power of minus 31 kg, and the value of E, that is charge on the electron, is 1.602 into 10 to the power of minus 19 coulomb. The value of H is 6.626 into 10 to the power of minus 34 joules second. So these are the constant values, and if you substitute all the values in this particular expression, so that is En is equals to minus 2 into z square will remain, and the value of pi is 3.142 whole square into 9.1 into 10 to the power of minus 31 into 1.602 into 10 to the power of minus 19 whole square, that whole divided by n square into 6.626 into 10 to the power of minus 34 whole square, right? So these are the constant values that we have substituted, and if you calculate this whole values, at final the value is going to be obtained in the value of in the unit of joules, and it comes to be minus 2.18 into 10 to the power of minus 18 joules. So this is the value of energy expressed in terms of joules. Okay, and we need to calculate the value of energy in terms of electron volt, not in terms of joules. So in order to convert the value of joules into electron volt, we need to know what is the value of 1 joule in terms of electron volt. So do remember, 1 joule is equals to 1.602 into 10 to the power of minus 19 electron volt. This is the value that we can use for converting joules into electron volt. Okay, so here we got 2.18 into 10 to the power of minus 18 joules whole multiplied with this constant, that is z square and n square. So z square by n square. So these variables are supposed to be substituted. Okay, so depending upon the values of n and z of the we will get the definite value of energy for that electron, depending upon the orbit in which it is present as well as the atomic number of the atom. Okay, so if you want to convert this value into corresponding electronic volt units, what we should do? En minus 2.18 into 10 to the power of minus 18 whole divided by 1.602 into 10 to the power of minus 19 into z square by n square. Okay, so if you do the calculation, at last it comes to be minus 13.6 into z square by n square, which will be in terms of electron volt. Here we got three expressions. One is which is completely represented with the constants, this one, and after substituting the values of all the constants, the one which comes in terms of joules, this expression, and finally the expression for an electron measured in terms of or expressed in terms of electron volts. So for the value of z and for the value of n, which can take the values 1, 2, 3, 4 and so on, we can calculate the value of energy of an electron present in any orbit. Okay, and this expression can preferably use for calculating energy of hydrogen and hydrogen-like species. That means the atoms or ions that consisting of only one electron. And now we shall do some simple numericals. Here we shall solve some simple problem. So let us calculate the energy of electron in first Bohr orbit of hydrogen in terms of joules, third Bohr orbit of beryllium 3 plus in terms of electron volt, second Bohr orbit of Li2 plus in both joules as well as in terms of electron volt. So first we shall solve for our hydrogen atom. So number 1. So let us calculate in terms of joule. So En is equals to minus 2.18 into z square by n square. So this is in terms of joules, right? So here hydrogens, for hydrogen the value of z is equals to 1 and it is asked for first Bohr orbit, so the value of n is also equals to 1. So finally z square will be 1 and n square will be 1, that is 2.18 into 10 to the power of minus 18. 10 to the power of minus 18, the value of z is 1 as well as the value of n is 1. So whole and solely the value of first Bohr orbit, that is E1, is equals to minus 2.18 into 10 to the power of minus 18 joules only. Okay, so let us calculate for the second one, third Bohr orbit of Be3 plus. So beryllium is having atomic number 4 and third Bohr orbit, so the value of n is equals to 3. So the expression should be used for calculating energy in terms of electron volt. So En is equals to minus 13.6 into z square by n square. So this can be expressed in terms of electron volts. So minus 13.6, the value of z is 4, so 4 4s are 16 and the value of n is 3, 3 3s are 9. So if you do the calculation of this one, the answer after calculation of this particular is minus 24.17 electron volt. So which is much higher compared to the electron which is present in n is equals to 2 and n is equals to 1. Because in a third shell, that is in E3 level, the electron possesses this much of amount of energy, but in n is equals to 2, the electron possesses 54.4, in a strictly speaking way, minus 54.4 joules of energy, electron volts of energy. That means as you move from the nucleus, the energy of the shell as well as energy of the electron present in that shell will also increases. So let us solve the last one, that is the calculation of energy of an electron present in second Bohr orbit of Li2+. For Li2+, the atomic number, the value of Z is 3, and since we are telling for second Bohr orbit, so the value of n is equals to 2. So we should calculate in both joules as well as in electron volt. So for E2, minus 2.18 into 10 to the power of minus 18 into Z square by n square. So here it will be minus 2.18 into 10 to the power of minus 18. The value of Z is 3 and value of n is 2. Z square, that means 3 square. So 3 3s are 9 and the value of n is 2. So 2 2s are 4. So if you calculate this values, the answer is minus 4.905 into 10 to the power of minus 18 joules. And we can express the same in terms of electron volt, just dividing this by 1.602 into 10 to the power of minus 19. So if you divide it by 1.602, you are going to get minus 30.61 electron volt for the same E2 level. So this is in terms of electron volt and this is in terms of joules. So in either of the way you can keep the values for the numerical values. And you can notice over here we are representing the energy of electron in respective shells, respective orbits. See, everyone know about one periodic property, that is ionization energy, right? So it is the minimum amount of energy that we are supposed to provide for the electron so as to make it to come out of the atom by avoiding the nuclear force, right? So if you want to remove an electron from the first shell of hydrogen atom, you are supposed to supply this much of amount of energy for the electron. And if you want to remove an electron from third orbit of beryllium ion, then you are supposed to supply this much of amount of energy in terms of electron volt. And the same thing you can apply for lithium ion in terms of joules or in terms of electron volt. So if you calculate the value of energy, that in turn will give you the information of ionization energy of the electron. Okay, so by knowing the values of ionization energy, we can make use of it in performing chemical reactions by a particular species. And that's about the derivation of expression for energy as well as the way of calculation of energy of an electron of hydrogen and hydrogen-like species in respective orbit. And that's all for the session. Thank you.